Today we're going to discuss statistical tests. It is a little bit of the wrap up of the first week of the bootcamp. And the idea is that we discuss a little bit experimental design. We give you an overview of probability distribution and how to estimate parameters of a distribution. Now we're going to use all this in order to do what you probably are going to do most often in the lab, which is to gauge whether an experiment that you performed supports a hypothesis that you have. And this is what usually is done in the form of a statistical test. And after that, then you are going to switch over and look at more multidimensional statistical analysis. But today is pretty much a summary or a conclusion of the previous lectures that you've been having. At the core of statistical tests is the assumption or the central dogma of statistics that the a small sample of a large population has, of course, the same characteristics of that population from where the small sample was taken. And we are going to define or calculate descriptive statistics of that sample from the population in order to infer the properties of the general population. And for example, this is important for statistical tests because if, say, you're going to try to figure out the effect of a drug on the weight of mice, you cannot treat every mice in the world with that drug, but you can treat a small sample size or a small sample of lab mice and then weight them and try to infer whether mice that took the drug had a different weight than mice that didn't take the drug. So again, you are assuming that these mice are representative of what would happen to all mice if you give the drug to all of them. To put it even more blunt, in the naked statistics, there is this silly example of Miller drinkers. And the idea is that if you give a Miller drinker Schlitz beer, they will not even be able to notice the difference. But again, in order to see if this is true, you are going to give you're going to give Schlitz beer to only a small subset of beer drinkers, and depending on what happened to them, you're going to infer what the general population of Miller drinkers will say about Schlitz beer. Again, if you are interested in the effect of a drug on cancer genes, p53 is a known regulator of cancer genes, so you want to, for example, understand whether p53 regulates the target genes of your drug, for which a typical comparison is whether the promoters of the target genes have a more dense or have more p53 binding sites than the general population of genes. So in this case, the general population is your null hypothesis, and the sample that you have, you are going to test whether it's significantly different from what is the regular population of genes and the density, for example, of p53 sites on those promoters. So to make it in a schematic fashion, hypotheses that you may have will be tested in a robust statistical way by proposing an experiment that have enough power, and we'll discuss power at the end of the lecture. And you are going to take, or you're supposed to take, an unbiased sample. That means a sample that represents well the full population. You can think that if the sample is biased in the sense that it doesn't represent the general population because it has a proportion of individuals that react different to the drug that you're giving, then any statistical test that you make will not reflect what the general population will observe or will react to the drug that you're giving them. So with the small sample that is representative of the population, you compute regular statistics, and you then try to infer or decide whether the parameters that you are inferring from that small sample are consistent or not consistent with the hypothesis that you have. And of course, this process is iterative because the results of the experiments are definitely going to inform and maybe change your experimental design. So this can be a recurrent loop or feedback, constant feedback to improve or refine your experiments. So the lecture will be organized by first giving you the basic concepts. What is a null? What is an alternative hypothesis? And how do you define a test statistics that allows you to decide whether the null hypothesis explains or does not explain the data that you generated to test that hypothesis? We're going to then explore the notions of significance. So when does the value that you obtain for the test statistic is low or high enough for you to reject your null hypothesis. Then we're going to discuss a little bit how to judge how well the tests are performing. And finally, we're going to touch a little bit of tests that might be applicable when the assumptions of the most common tests do not apply. So in hypothesis testing, we are going to make a conclusion about a property or the phenomena we're studying. And in general, we are concerned of whether or not there was an effect in the experiment that we carry on and whether that effect is consistent with the hypothesis we have. And we set up this hypothesis testing by proposing two mutually exclusive alternatives. The null, which says that there is no effect, your hypothesis is wrong, or whatever you're measuring is not consistent with your hypothesis, and the alternative hypothesis says there was an effect. So in the case of the knockout mouse, we would say that the null hypothesis is that the knockout gene, that the gene has no effect on weight, and hence the null hypothesis there is no difference in the weight of the mouse compared to the expected weight of the population that we have measured before. And the alternative, of course, is there is a change in the weight. So the mean of the weights for the mice that have a knockout gene is different than 25 grams. There are two ways to think about hypothesis testing. The most common one is to compute the likelihood of the data given the null hypothesis. And whenever that likelihood is small, we reject that hypothesis. This is the frequentist approach and is the one that is most commonly used. But a more intuitive approach that is just computationally much more complicated and that requires assumptions that we generally do not want to make is to, instead of judging the data or the data based on the hypothesis, is the reverse, is how your belief or your confidence in the null hypothesis changes after you have obtained the data from your experiment. And this is what you may have heard before as the Bayesian approach. But again, we are not going to cover that in this course. This is something we cover in our more advanced courses. But suffices to say that for the frequentist approach, we are going to put a threshold, a significant threshold alpha, and whenever the likelihood of the data, given the null hypothesis, is less than that significant threshold, we reject that hypothesis. And we think that the alternative hypothesis might explain the data better. And then we take it. So in our knockout mice experiment, if we have measured that the weight of mice in general, in the general mice or laboratory strain population is 25 grams, the null hypothesis that the knockout has no effect is that the weight of the mice that have a defective gene will also be around 25 grams. And of course, the alternative hypothesis, being the complement of that hypothesis, is that the mean of the weight of the mice with a knockout gene is actually not 25 grams. So let's go through this process in detail. So we have set up a null hypothesis H0. That hypothesis actually is numerically tested. So it is, although our hypothesis is about general effect on mice weight, we have made a very concrete and very specific statement about the weight that we would expect or that we think mice would have when our null hypothesis is true versus when it's not. We are going to begin our hypothesis testing, and as we discussed before, the frequentist approach to hypothesis testing is going to try to determine whether the data that you collect is consistent with that null hypothesis or not. And the alternative hypothesis, the one that actually is your hypothesis, the one you are testing, is that the control mice will have a different weight than the knockout mice. And that hypothesis is not an equal sign. It's a different sign or a greater than sign. That's what an alternative hypothesis would use. And this is, again, the hypothesis that you believe it is to be true, and the hypothesis that actually you are testing against, or that you generated data to test. The book defines hypothesis testing as a way in which you can compare the data to the expectations that you have given a null hypothesis. And whenever the data is too unusual in that hypothesis, then you reject it. So this has pretty much three different components. There is a way in which you need to compare the data. And comparing the data is done using a test statistic. And we will define what these test statistics are in a second. And the second part of hypothesis testing is you need a distribution. And this distribution of the test statistics, so you can determine when this value that you obtain is rare enough for you to reject that hypothesis. And finally, you need to compute this probability, this likelihood of the data given the hypothesis, so you can decide whether or not that null hypothesis can be rejected. A test statistic is a quantity that you compute from your data and allows you to distinguish between the null and the alternative hypothesis. And in parametric tests, that is a lot of what we're going to discuss, at least in the first 3/4 of this presentation, you must know the underlying distribution for that test statistic. And that is important so you can compute or estimate how unlikely that value is under the distribution for that test statistic. There are common test statistics that you probably have heard before. So the t-statistic is typically used to compare means to see if, say, two populations have or do not have the same mean. The number of successes on a trial is a typical test statistic when you want to estimate whether the samples that you have were drawn from a distribution that have a known or previously estimated probability of success. And the book has a beautiful example for that, which is you want to determine whether fish that are infected by a parasite are eaten more than healthy fish. So this is a typical case where you estimate P from the natural population and then sample from fish that are infected by a parasite and see if the number of successes is consistent with the frequency at which fish are usually eaten. You can also compare several samples and determine whether any one sample has a different mean, and for this you can use an F statistic. Let's revisit a little bit the central dogma of statistics that we discussed briefly at the beginning to put in context what we are going to do as we do statistical testing. So recall that we really care about the population, but we cannot test the population. We also assume that there is something like weight that is what we want to understand that is or is not the same in the general population versus whatever treatment you gave or you're planning on giving to that population. So because we cannot study the population as a whole, we need to study a sample of the population, which, as I mentioned before, has to be unbiased. And we are going to try to infer the parameters of both of the population that we treat by estimating the parameters that are underlying, say, the weight of mice treated with a drug or adults vaccinated against COVID-19. And those descriptive statistics that are shown here in the table to the right are the ones of which we're going to test. But those are sample statistics, and the test statistics are based on those sample statistics and try to determine whether the difference between the sample statistics on, say, a control sample and a sample that you treated with a drug are sufficiently different in order for you or to reject or to conclude that the null hypothesis does not explain the data appropriately. So what about the expected distribution of the test statistic? That's the second important piece of statistical tests. Two theorems in statistics allow us to understand better the underlying distribution of test statistics. And the big theorem is, as the Naked Statistic book repeatedly reminded us is the central limit theorem. And it says that given enough observations, then the sample mean as a statistic distributes close to a normal distribution. And the second theorem is the law of large numbers that says that if you draw enough samples and the sample size is large enough, then the mean of those observations is going to be close to the underlying population mean. And what's that number? What is that large number? Well, it really depends on the underlying distribution of the samples that you are drawing. But as a rule of thumb, if you have more than 30 samples, then both laws tend to comply. And I'll show you examples where if the underlying distribution is really, really not normal, then the compliance is much less. And I also encourage you to play with applications that show you how these two laws apply in different cases. One of the most common statistics used to determine whether your sample is different than what you would expect and to reject then the null hypothesis is the t-statistic. So if we go back to the example of this knockout gene that we think affects mouse weight, and we have computed the weight of the wild-type population to be around 25 grams, and we generated a sample of knockout mice which we weighted, and now we want to compare or determine whether their mean weight is significantly different or different than the wild-type weight. Then a standard way to test that is using, or a standard test statistic is the t-statistic described below, which, if you look at the formula, tries to first estimate the standard error around the mean, that's the s divided by the square root of the number of samples, and then tells you how many standard deviations of this estimated error around the mean the computed mean is from the theoretical mean. So in our case, if you just plug in the numbers and you have an estimated or a measured mean of 29.8, then the t-statistic for that sample will be around 596. And we'll see in a little bit how we measure or how we estimate how rare or how non-explainable by the null hypothesis this value is. If you know the theoretical standard deviation as well, then another way to test the same hypothesis is using the z-statistic, which, if you look at the formula below, is again very similar to the t-statistic, except that instead of estimating the error around the mean, you use the estimated population standard deviation to compute the test statistic z. And again, we'll look in a little bit what are the differences and when to use one versus the other. So next we're going to discuss when or how to determine whether these numbers, for example, the t-statistic value that we have before, is significantly non-expected or very unlikely under the null hypothesis, and also discuss other common statistical tests. Going back to the knockout gene example, we had discussed the null hypothesis of the mice, of course, weighting the same as the wild type versus the mice not weighting the same. So your hypothesis can be a little bit more subtle. You can hypothesize that the loss of the gene makes mouse more obese. In that case, we call this a directional test, and it's one in which you hypothesize, as opposed to the hypothesis we have been discussing, that your mean of the control of your samples is actually greater or smaller than the wild type. So that's what we would call a directional test. And either directional or non-directional test, what we're going to discuss next is how do we evaluate the statements, how we decide whether the sample that we have is consistent or not consistent with the null hypothesis, or whether we can reject it. A probability value, or p-value, is the metric used to determine the significance of our test statistic. And it is exactly that. It is the probability of observing the computed test statistic or the sample test statistic under the hypothesis that the distribution from which that value was sampled was the null distribution. And whenever that value is less than a significant threshold alpha, you reject the null hypothesis. And whenever that value doesn't reach that low level, then you are unable to reject. Doesn't mean that the null hypothesis is untrue. It just means that your test, your data did not reach the significance level necessary for that rejection. So the conclusion is you cannot reject. Doesn't mean that your null hypothesis, your alternative hypothesis is not true. So this significant value is usually in this significant threshold usually determines what we call a rejection region. Any value observed on the test statistic that is in that rejection region is going to be could be enough evidence for us to reject the null. So let's go back to our knockout experiment setting and discuss how to compute the probability value or p-value of the t-test statistic that we obtained that was 5.96. So is that value, what's the probability of obtaining 5.96 if the sample that you had distributes according to the null distribution? That means whether the t-statistic, that 596, comes from sampling from a t distribution. So the observed data point 596 is shown here at the bottom right corner of the green area, and the p-value is just the probability for this one-sided test for asking whether your sample supports the idea that mice with a knockout gene are heavier than wild-type mice, is the probability of obtaining 596 or any value larger than 596, and that's the region under the t distribution, that is density function, that is shaded here in green, and that is and how unlikely is the value that we obtain, how unlikely is this 5.96. So we'll compute that value in a second. On a two-sided test, but also on a one-sided test, once you establish a significant threshold and you know the distribution of the test statistic under the null hypothesis, then you can always define what we call the rejection region, which is the values for the test statistics that will lead to a rejection of the null hypothesis. And that critical values are the value such that any value that is less or greater than your critical values will automatically result into the rejection of the null hypothesis. And here we see them shaded in red. So going back to our example where we computed the t statistic to be 5.96, we wonder now whether that value exceeds the significant threshold, say 5%. So to compute the significance of our t-statistic value of 5.96, we want to compute that area under the curve of the t distribution for 19 degrees of freedom. And I want you to point to Kathleen's lecture on distributions, where she explained how the t-statistic is dependent on the number of observations that you made, and that number of observations is one greater than the degrees of freedom of the underlying t-statistic for that sample. And there are tables available that give you the critical value. Remember, critical value is that point after which your observations will be in the rejection region. And for our case, the table we'll look at will be for the 19th degrees of freedom, and you can see that even for 0.005 rejection region, a value of 383 will suffice, and our statistic is much greater than that. And indeed, the probability of observing a 596 on a t distribution of 19 degrees of freedom is less, or it's about 10 to the minus 5, so we can comfortably reject the null hypothesis for our case. I just want to make also a note that you should not overinterpret the magnitude of your p-value. A tiny p-value doesn't mean that the result is more important than a result that has a less impressive p-value. P-values are influenced by many factors that are not related to the biological importance of your result. For example, a knockout gene that has a huge effect might have a relatively modest p-value if your sample size was not that great. On the other hand, a gene that really has a tiny effect might have a ridiculous p-value because you sampled a lot of mice. It is also important to know that the p-value does not reflect the probability that the sample mice weight was the same as the wild type, nor it says that what is the probability that your experiment was a fluke and that for some reason you got the result that you wanted, but it might not be true. Nor does it say that you were that if the p-value is not so low that you were wrong in deciding that our sample mice were weighing more than the wild type mice. Again, what the p-value says is what is the probability that our observation on the knockout or knockdown mice is different than the weights of the average wild type mice occurred by chance if the gene has no effect. Again, as I mentioned before, and I want to reiterate it, statistical significance does not imply scientific or biological significance. In scientific significance, as I mentioned before, is how relevant, how important our result is to understand nature or to understand a phenomena. And many things may be statistically significant and might not be that interesting. A tiny effect on our gene could be really statistically significant if we sample enough mice, but it may not really impress anybody or yourself because a tiny effect might not really explain much of the biology. Again, statistical significance, as we mentioned, is this surprise factor under the null hypothesis. And as I mentioned before, is affected by many, many different things. So we need to be really careful when we interpret what the statistical significance of our result is. Going back to our favorite example of a knockdown gene, we have been using what we call a one-sample test because we assumed that the population mean was established and we had measured it before. This is in general not how we set up the experiment. As Athma discussed in the first day of the bootcamp, your experiments usually want to control for the housing of mice and your diet and many, many different things. So in general, your experiment would have used mice that are knockdown as well as mice that have a wild-type version of the gene. And you would have weighted both the control and your knockdown mice. And you wanted to compare the means between the two groups, which actually control for all these extraneous factors that you are not interested in measure, and the experiment will be more robust. So this is what we call a two-sample t-test. And in a two-sample t-test, you don't even need to have the same number of mice in both samples, and it actually controls for the differences in the two groups. Your experiment might not have been perfect. You might lost a wild-type mice. And there are two types of these two-sample tests. Either you have two groups of separate mice, like the one we are describing, where there is a group that has knockdown and a group that has wild-type gene allele, and they are not related at all. But there are also more powerful tests that can be done in certain circumstances called a paired two-sample t-test. And that's, for example, if you're giving a mice a treatment. So you can have the same group before and after treatment, and you can now test whether the difference between the mice before and after treatment was significant. And that is called a paired two-sample t-test because every observation in both groups is related to each other, and that gives you a little bit more power to determine whether the differences are significant than when you have two unrelated groups in the unpaired two-sample t-test. So your experiment might not be perfect. Your data might not result in you rejecting your null hypothesis, and the null hypothesis might be wrong. Your hypothesis might have been true. Conversely, for some weird reason, your data was very an outlier with respect to the null distribution, and you may reject your null hypothesis when the null hypothesis is true. So let's discuss a little bit of these two scenarios and what we call statistical power, which is how do you design an experiment that whenever your data supports the alternative hypothesis, you are going to be in fact able to reject that null hypothesis. And that is what usually is called statistical power. Then let's also discuss a little bit about what happens when you do like high throughput experiments or genomic analysis where you are testing many different hypotheses simultaneously. How do you correct for that fact? So we'll discuss this too in the next 10 minutes. So let's think about rejecting the null hypothesis when it should not be rejected. So it could just be by total chance, right? Because our significant threshold is arbitrary and also set at, say, 5% in this example. And yes, there is a 5% chance that your data falls into that rejection region, that the test statistic value is in that 5% rejection region, yet the null hypothesis might be true. It's just that by this weird luck of life, you got an experiment that was at the tail of the null distribution, and you would reject the null hypothesis when that hypothesis was not to be rejected. So again, in our case, the value is so much rarer, so the probability of that false rejection is much lower. So what we really want is we really would like to do not reject the null hypothesis when the null hypothesis is true, and ideally our data will reject it when you should reject it. And the two types of errors is when you actually reject it when it is not to be rejected, that low left corner, that is called a false positive, where you actually think something is consistent with alternative hypothesis when it's not. And a false negative is when your experiment, the data that you obtained, it is not doesn't fall in the rejection region, and you hence did not reject the null hypothesis, and when the null hypothesis was supposed to be true. At a significant threshold of alpha, say 5%, the correct decision, if the null hypothesis is true, is of course 95%, right? So 95% of the time your experiment will be outside the rejection region, and you will accept the null hypothesis. You will not reject the null hypothesis. And of course, your type 1 error rate, or the fraction of times that your data will reject the null hypothesis, will occur 5% of the data, or alpha, and that's the rate at which your type 1 error you will incur into this type 1 error. Let's call beta the probability of not rejecting the null hypothesis when the null hypothesis is false. So 1 minus beta is the fraction of times that you actually correctly reject the null hypothesis, and you want to design your experiment so you have enough power, right? That your data, whenever doesn't support the null hypothesis, is far away from it that you can detect it. So that is usually what we call power. 1 minus beta is a fraction of time where whenever the null hypothesis is false, you actually are able to reject it based on the data that you have. So you want to design experiments that allow you to have enough data, enough replicates, enough samples, enough whatever you need in order that whenever the null hypothesis is not true, that you are able to correct. You have enough power to reject the null hypothesis. So why not design experiments that are perfect, that where you will never fail to reject the null hypothesis when the null hypothesis should be rejected, and when you always reject it when it should be rejected? Why can that be done? And the reason is that beta and alpha are intrinsically related, and usually by being more stringent and say to minimize your type 1 error rate, you tend to also incur more into type 2 errors, because if you are very stringent in order to reject your null hypothesis, you are likely to miss sometimes where you should reject the null hypothesis. And you can play a little bit with it. It is super useful to try to understand how intricately related they are by looking at that shiny apps or that website that we are referring to below. So ideally, you really want to minimize. So when you design an experiment, it is one of the most important things. And if you ever are going to write a grant and you propose an experiment, one of the things that reviewers expect you to discuss is how you're going to be able to design or propose an experiment that actually is able to reject the null hypothesis if such is true. And that is called that you have enough power to do so. So if your budget is small and you don't propose enough replicates, you might not be able to detect differences in the mean, for example, between your knockout gene and the wild type if those means are close to each other. You need to provide an experiment that has much more replicates in order for you to be able to detect the differences that you might expect. And if the differences are small, you might require a greater sample size, or if the variance in your measurements are high, you might require a larger number of replicates to be able to have enough power whenever you get your data to reject the null hypothesis if the null hypothesis is true. So power analysis enables sensible experimental design and enables you to, at least under the assumptions that you have, to be able to reach the conclusion that supports or doesn't support the hypothesis that you are testing. It is common to aim for enough power, 80% power, to reject the null hypothesis. That is considered a sound experimental design. So let's visualize this a little bit. So say you have two populations, your control population 1 and your knockdown population 2. So what factors affect, say, your power, your type 2 error rate? So depicted here are the density distributions for, say, the weight of these two animals. And you can see that if the critical value is right there where the arrow is pointing, then any value that is on that blue part could be expected, or not expected, but could happen at the significance threshold that we place, even under the null hypothesis, because for some reason your experiment happened to sample an extreme value for that distribution. On the other hand, the orange or the pink shading is all the values on your experiment that, if you obtain them, will actually lead to a rejection of the null hypothesis, and these will be the power that you have for rejecting the null hypothesis. It is interesting that as the means get close to each other, your power increases, your power decreases. As alpha is greater, then you are moving your shaded pink to the left, but you are also incurring in a higher type 1 error rate. So changing your significant threshold will increase your power at the cost of also increasing your false positive rate. There are other things that impact. Another factor that dramatically affects your power is the variance, the variability of your measurements, because the more variable they are, remember our t-statistic, the denominator for that t-statistic was the sample variance, or the error around the mean, and the greater that is, the smaller your t-statistic is, for example. So your variance, your variability on the data greatly decreases your power to detect. They are inversely correlated. Similarly, the effect size is another factor that dramatically affects your power. The greater the difference between the two populations, the greater your power, and the lesser your difference, the more the more difficult will be to determine or to reject the null hypothesis in an experiment. To summarize what we just discussed, the false positive rate is determined by your significance threshold, and usually in biology a 5% significance is what most people use. The power is the fraction of times that you are going to actually reject the null hypothesis when you should have rejected the null hypothesis. And for most applications, power of around 80% in your experimental design is what is most recommended for a typical experimental design. And things do change dramatically when you are doing a large experiment. For example, in RNA-seq or in high-throughput compound testing, you are basically, say in our example of the knockdown gene, if you're instead of just looking for the weight of your 2 mice, if you're trying to understand what genes are affected by the knockdown of the gene that you want, or how many genes are affected by the drug that you gave, or in a high throughput screening, which compounds do affect the weight of the mouse, and you screen 2,000. Now, you are going to have a different problem, because although the probability of rejecting the null hypothesis or saying that a gene is differentially expressed, that is the null hypothesis that the gene is not differentially expressed. Now the probability of each one is still 5%, but you're testing thousands of them. So the probability of observing that outlier, even under null distribution, is not trivial. In fact, if say at a 5% error rate, you would have, if you test 1,000 genes, you would definitely have at least, just by chance, 50 genes that exceed your threshold because you sample so many times from the null distribution. So let's do this a little bit slower. So if we have M hypothesis tests, say we tested M compounds, or we are testing 10,000 genes, for example, or 2,000 compounds, what is the probability of at least one false positive, meaning that you rejected the null hypothesis when you shouldn't have? So say M is 10,000, and say there are no time where you should reject the null hypothesis. Then if because of the probability of making an error is 5%, and of course the probability of not making an error is 95%, then the probability of not making an error in M tests is that you didn't make a probability ever, right? So you didn't make a probability in the first, and in the second, and in the third. And if you recall your probability lecture, the probability of the union of events that are independent is the product of the probability. So it's 1 minus a to the m. It's 0.95 to the 10,000, which is an extremely tiny number. So you are almost guaranteed to have at least one false positive. And as this chart gives you, it's the same as we just did before. The probability of at least one false positive is quite high even for low m's. And that is why a multiple hypothesis test correction is needed whenever your experiment or your investigation requires the test of many different hypotheses in the same experiment. And one way to do this is to adjust the p-value. So you kind of take into account the fact that you're going to do many independent tests, and you change that threshold to reflect the number of tests that you make, and in order to control or to reduce the error at which you're going to make a type 1 error. And that is called, again, multiple hypothesis test control. And there are many different ways to do this. And there are two that in the 90s were quite popular, or that's not only popular, that actually set the way in which we think about how to correct this false positive error rate. And the first one that came out is a family-wise error rate. It is to actually try to avoid or estimate the probability of making one error rate. That was the first, and it's a more simple but actually more stringent way to control your false discovery rate or your type 1 error rate, not your false discovery rate. The second method that was developed later to address the fact that the family-wise error rate was too stringent is to actually have a probability or a threshold that actually in which you were able to say, okay, I'm going to incur into a fixed number or a fixed fraction of false discoveries at whatever significant threshold I choose. And I'll get into that a little bit, but that decreased the stringency with the cost that you know you are incurring in false discovery, but you are controlling the fraction of all your calls that actually are type 1 errors. To control the family-wise error rate, or to ensure that the probability of making one type 1 error stays at the same significant threshold as that you wanted to begin with, the Bonferroni correction achieves that, and it's an adjustment on your p-value. So if you want to ensure that even if you make m different hypotheses, the probability of a false positive is still alpha, even though you are now making many hypothesis tests at the same time, you can do simple math. And I think you intuitively know what the correction should be, because you want to ensure that even if you sample m times, you still want to be away from that rejection site. And if you construct your significance threshold by dividing your original significant threshold by the number of tests that you make, you can see that you ensure that the probability of still making one error is the same as it was for one error when you divide by the number of tests that you make. And that is the family-wise error correction, which is quite stringent, because if, for example, you apply a family-wise error rate on your differential gene expression analysis, you're going to divide by 20,000. So you have to achieve 5, almost 10 to the minus 6 significance in order for you to call a gene differentially expressed, which probably you're not going to have power with. So because of that stringency in the family-wise error correction, people started to think about ideas on how to not just avoid any error, but to control the number or the fraction of errors that you would incur at a certain significant To reduce the stringency of the family-wise error correction, what Benjamini and Hochberg, which is the method that we're going to discuss, propose was to control for the number. So to control for the number or the fraction of the false discoveries in your data. So this is it's a beautiful idea. If you order the p-values of your data and suppose you have no signal, then the fraction of points or observations that you would get at the jth p-value is roughly j over the number of observations. So if you want to control and keep that fraction of false positives tight at, say, delta for your false discovery rate, then you want your p-values to be not less than just the fraction of observations, but delta times the fraction of observations. That will ensure that you only have delta false discoveries at that p-value. And that is what Benjamini Hochberg proposed. And let's see a little bit. So how does it work? In reality, what you do when you do differential gene expression analysis is that you compute both the p-value and the FDR correction, and you can see how useful it is. this is a set of replicates that are all from the same condition, so you should not call any differentially expressed gene. You can see that at nominal p-value, some genes by chance will exceed the significance threshold of 0.005. But if you do an FDR correction at the same significant level, at a 5%, meaning that you are only willing to call 5% of differentially expressed genes that should not have been called, that are not differential, but the 95% you are okay with, then you actually, in this case, would not call anyone. So the correction actually works quite well for this example. So just to summarize how all this works, there are different ways in which you can control for the problem of doing multiple independent hypotheses in the same experiment. And if you do not correct for multiple hypothesis testing, then you will actually very rarely fail to reject the null hypothesis when it should be rejected, meaning that your false negative rate will be tiny. But that will cost you because you will have a high incidence of false positives. You will be rejecting the null hypothesis many times when you should not. So the false discovery rate that I just mentioned last, the Benjamini-Hocher method, actually is a mix, right? So it allows for some cases in which you are going to reject the false hypothesis when should not, but it reduces drastically the number of false negatives. On the other hand, on the other extreme, family-wise error correction in the Bufferoni correction will eliminate the false positives at the cost of reducing dramatically your power. So usually, in general, false discovery rate is the ideal method to account for large experiments. So I just want to make a brief note that some of the tests that we discussed, like the t-test, assumes some normality, either a huge sample size or some normality, and huge deviations from the normality will make the t-test perform poorly. So when the assumptions for a test are not met, that's called, and a t-test assumes a distribution, that's what we call it parametric. The distribution is it's parameterized by that distribution. The test is parameterized by that distribution. Then we cannot do a parametric test. We have to do a non-parametric test that makes no assumptions under the underlying sample distribution. And those tests usually have less power than the parametric test. So if you can make the assumptions, the parametric test is. And this is just for completion. These are examples of parametric tests, but let's just look at one. So suppose you have a way to measure attention span or the ability to concentrate on a class. And the lower that score, the more concentration that person had on the class. And you are trying to test whether there is any difference in the ability of concentration between females and males. So there are two possibilities. And this distribution has nothing to do with normal. It's very skewed, so you don't want to you measure for males and for females, but you do not want to do a t-test because you didn't have enough measurements, and you know that the distribution of your score is highly non-normal. There are two possibilities, right? The distribution overlap, the left one, or they do not overlap. So females, say, have a better ability to concentrate. So the Mann, Whitney, Yu, or Wilkinson ransom test can address that, and it's an alternative to the t-test that is kind of super intuitive, because what it does is it tries to see when you rank your data whether the ranks are intermixed, right? So if the way in which you split your data, in this case females and male, has no inherence or has no difference in the test, the ranks should be mixed. And if there is a bias, if there is an effect of the sex in the ability to concentrate, then one set will rank in the top and the other one in the bottom. So in our example, say males have a lower score, so they rank in the bottom. So you order your tests from lower to higher. And the first two columns are the test broken by male and female. The second two columns are their ordered scores, and in the last two columns are the rank of those scores. And whenever they tie, you assign them the middle rank. So the U statistic, you sum all the ranks for all the data that you have, and you subtract the sum of the ranks for the set of observations for that group, and you take the minimum of the maximum. I think the maximum of those two ranks, and that's the U statistic. And you can look at the significance of your statistic on a U table and compute a p-value like we have done before. And the p-value will not be as powerful as a t-test if you could have done, but it's a way to determine whether the two distributions for the two groups are different. There are other tests to compare distributions. The famous Kolmogorov-Smirnov or KS test tries to look at differences in the distributions in the cumulative level. So if you have two cumulative distribution curves, the Kolmogorov-Smirnov statistic is the largest difference between the two cumulative distributions. And again, there is a table for these values, and whenever the difference is too large, then you reject the null hypothesis that the two distributions are the same. So this is a test that directly compares two distributions. There is really no free lunch in hypothesis testing. The power of a test depends on your data and the distribution that underlines your data. There is really no one best solution. You have to explore and understand your data in order to apply the best test that applies to your data. The non-parametric tests are beautiful because they have very few assumptions, but the power to detect difference is reduced. Tests have really variable efficiency in detecting significant effects. And you usually do much better with parametric tests whenever the conditions are met. And the Mann-Whitney-Wilcoxon test is one of the best to detect changes when the conditions are not met for a t-test or a z-test. There are beautiful visualizations that I encourage you to look at the concepts we have given you. There is no better way to understand this but by playing with data. So just please go to these sites and play with the data. And AFMA put together most of this presentation with some previously material from previous material from the people that we are thanking. And we'll talk tomorrow about your questions on this material.